What's up, guys? This is concept 17, discontinuities in the graphs of piecewise functions. Um, so apologies ahead of time if you hear my dog eating, drinking, or if you hear some of the music that's playing outside, or anything like that. Also apologies for the mic quality. Sometimes it just sounds awful, but anyway. Um, Here's the first page. You can pause it here so that you can start writing this in your notebooks. Also, this might not be the accurate page number. I think we're like on page 43 or 44 or something. Okay, so we can predict without graphing the behavior of the graphs of the pieces in relation to each other. There are three different scenarios. The first scenario, pieces can connect at a closed circle at x is equal to a. So I'm just taking some arbitrary graph here. So, let's say somewhere on the left side of the x-axis we have a absolute value that's being reflected across the x-axis, so it's pointing downward. And then at some point, let's say here, it's going to meet, I don't know, like a parabola of some sort. So that x value would be a. It's negative a. So this piecewise function, an absolute value, and a parabola, a quadratic, met at a closed circle. No discontinuity there. Okay. So in scenario B, the pieces can connect at an open circle. So let's take the same graph here so that we can see like what the difference would look like. So I have some absolute value. However, instead now here at A, we're going to have it connect at an open circle. Okay. Then in scenario C, the pieces cannot connect with each other at all at some x for A. So what would that look like? So might start off the same. Heck, we could probably make that a closed circle, whatever, at A. However, that parabola piece, it's not connected to it, so it'll do something like this maybe instead. Okay, so those are the three scenarios. Next here, it'll say the latter two of these three scenarios are examples of functions that have discontinuity. So the first one is continuous. Okay, there's no breaks. In other words, you can trace it with your pencil and there are no missing parts or jumps. Here, right, as I'm tracing with my pencil, I would run into a problem. There's a missing piece on the graph. There's a gap. Okay, I would, if I was walking along this, if this was like a map and this is a trail, I would fall into the hole. Okay, this is a discontinuity. Here, as I'm walking along this piece, like if that's a trail, once I reach here, it's like a dead end. There's no way for me to be able to continue here and keep going along my way. Okay, this is also a discontinuity. So continuous, discontinuity. Okay, pause it so you can write this in, and then we'll go ahead and do it. I didn't want to draw in the graph so that we can actually practice drawing in the piecewise functions. I know that's still a hard topic here. So first piece I have here, it's a quadratic, so it's going to be a parabola, and it is reflected across the x-axis, so it's going downward. And then the second piece is an absolute value function. That's the v, right? Here's my domain for each one. So for the first one, normally a parabola opens up from the center up, right? But this one has been shifted 3 to the left. X plus 3 would be 3 to the left. So 3 to the left, and then plus 4 up 4. Okay, so that's where the vertex is. Instead of opening up here, okay, it's going to be opening downward here. So let's plug in the endpoints now just to get the general shape of the graph here. Negative 5, I'm going to plug this in here. Negative 5 plus 3 is negative 2. Negative 2 squared is positive 4, but I still have the negative. So it becomes negative 4. Negative 4 plus 4, 0. So then at x negative 5, that's what I plugged in, I got 0. So I'm right on the x-axis. Okay. Next one is the 0. Also, sorry, gotta mention, I plugged in negative 5, x is less than, greater than or equal to it. So it is a closed circle. Okay. For this one, x is less than 0, but not equal to it, so it'll be an open circle. So if I plug in 0 here, 0 plus 3 is 3 squared, 9, but becomes negative 9 plus 4. So at x0, negative 9 plus 4 is negative 5. So I would go down to negative 5. At x0, it's kind of hard to see there, but it's an open circle. Okay, it'll be open. So carefully then, draw in the rest of it. I don't go past it because it's from negative 5 to 0, right? So I do stop there. Then, if you're not sure where it's crossing towards the right here, a parabola is symmetrical, right? This is at x3, so 2 to the left is crossing the x-axis, so then that means 2 to the right, it's also going to be crossing the x-axis. Okay, so here's my parabola. Let's make this a bit more rounded. Okay, then I have this absolute value. It's the V shape, 2 to the right, so instead of going from the origin like this, I go 2 to the right, down 7. So this was negative 5, negative 7, so here's where the vertex is of my absolute value. Plug in the endpoint, x0. If I plug in 0 here, 0 minus 2 is negative 2, but absolute value of negative 2 is 2. 2 minus 7 will be negative 5. So at here, this will be negative 5, and it is a closed circle. So it was once open, but now because of the right piece here, it closes. Okay, notice that the slope here, it is symmetrical, right? So it goes up 1, left 1, so you can do the same thing to the edge here, and it is for all x is greater than 0. So for this piece here on this end, it does go forever. Okay, now it says the first piece of the graph of q of x will end at, so they're talking about this one, okay, it ends at x is equal to 0, because from negative 5 to 0, that ends just shy of it. The second piece of the graph of q of x will begin at, so then if this one ended at 0, the next one began also at 0. Okay, is q of x defined at the x value where the first piece ends and the second piece begins? So they're talking about at x0. So is it defined? Does it exist, in other words? If so, find the value of y at that x value. Okay, so we just showed, right, by graphing it, that we closed the circle, so it is defined. So let's just show it algebraically. So at q0, it is q of x. Okay, let's find the y value. I don't plug into the first one because the first one does not include 0 in the domain. I have to plug it into the second piece. So this would be the absolute value of 0 minus 2 minus 7. Okay, which becomes then absolute value of 2 minus 7, which is 2 minus 7, which is negative 5. Okay, this next thing we see here, posit 2, sorry, I don't remember if it was visible, if you need to write it in, What this means here, this is end behavior notation. Okay, what this is saying is as x approaches 0 from the negative side. So as the x's approach 0 from the negative side, q of x approaches, what's the y value as I approach x0? It's -5. Okay, so again, as I approach x0 from the negative side, where is that point on the graph? What's the y value of the point on the graph? -5. Okay, as x approaches 0 from the positive side, so now I'm coming from here. As I approach x0, what's the y value of that point on q of x? Q of x approaches, same thing, -5. Okay, as I approach 0, I approach the same point, -5. Okay, so determine the y values. I don't even know why. Determine the y values of each piece. Yeah, this is one terrible typo. Determine the y values each piece approaches from the left and the right at x0. So then how would you show this? This is like how a free response might ask you. You're going to say as x approaches 0 from the negative side, q of x approaches, okay, and then you're from the negative side, so you're going to have to plug into the first piece because that's from the negative side. Okay, that'll be -0 0 plus 3 squared plus 4, which becomes, use the arrow notation because we are showing end behavior. Okay, as x approaches 0 from the negative side, q of x will approach. Okay, we plugged in 0 plus 3 is just 3. 3 squared is 9, -9, plus 4, which is -5. Okay, as x approaches 0 from the positive side, q of x approaches. Now we got to plug it into the second piece, okay, because this is the right side. Okay, so then this will be absolute value of 0 minus 2 minus 7, which becomes 2 minus 7, which is -5. Okay, so again, we're determining the y values of that each piece approaches from the left and the right of x0. So since, you can say now, you can say since both pieces approach the same y value of -5 and q of 0 is equal to -5. We show this right here. Okay, it's in the domain, in other words. Then q of x is continuous at x0. We just showed there's a closed circle and the pieces connect at a closed circle. Okay, that's what this statement here just showed. Again, there's a closed circle and the two pieces meet at a closed circle. We just showed scenario A. Okay, so not always will you have the graph or be asked to graph it to be able to do the analysis. Sometimes just strictly algebraically you can determine if the graph, whatever it might look like, will be continuous at a certain x value. So the next page here, okay, is this one. This one, it goes pasted in the notebook. Okay, and we don't really do much in this page aside from the top here, the graphic organizer, but we are going to be referencing it for the next like 2 pages, I believe. Okay, so We have two types of discontinuities. The first one, we call it a jump. Okay, this means the two pieces do not connect. Okay, we have an example of this first type of discontinuity here on the first graphs for f of x and g of x. Right here, again, treat it like it's a path, right? You'll jump to get to the other piece. Here, same thing, when you reach x negative 3, you'd have to jump. Okay, so they're not connected. Okay. For the next type of discontinuity, we call this a point discontinuity. It's also called sometimes removable discontinuity. This means two pieces connect at an open circle. Okay, if two pieces connect at an open circle, we have examples of that here. H of x. Okay, as you travel along this path, you'll bump into an open circle along the road. You'd fall in. Okay, they're not connected per se. Okay, they meet at an open circle. Same thing is happening here. Okay, for P of x, there's an open circle there. So then it's not smooth, it's not continuous, right? There's a missing part of the road. Alright, so we jump into the next page, and again, we'll be referencing this as we do the next parts of the notes. Pause here, write this in, okay, and we will continue. So for f of x, it says, the first question, what type of discontinuity and x value, the type of discontinuity and x value where it occurs. So for f of x, that's the first graph here, right? The discontinuity is happening at x3, okay, and this is clearly a jump. They're not meeting at all, okay? So then what you're going to say is jump at x is equal to 3. Okay, next, is f of x defined at this x value? If so, what is the y value? So you can do this graphically or through the function equation. Notice that for x3, right here, it's not equal to it, right? So then you know you're going to have an open circle for the left piece, and you do right here. You meet it's an open circle. Then for the second piece, this one, 3 is also not in the domain, it's not equal to it. So it'll be an open circle, and it is. Okay, so 3 is not in the domain for either piece. So then you could say f of 3 is undefined, or f of 3 equals undefined. Okay, so next one says the first piece stops at x is equal to. As you go through the first piece, okay, right here, it stops at x is equal to 3. And the second piece begins at, here's the second piece, oops, and it also begins at x is equal to 3. Okay, next one, end behavior. As x approaches 3 from the negative side, so as you approach 3 from the negative side, okay, so the left side, as you approach 3 from the left side, what is the point on the graph? What's the y value? It's the open circle, and then that y value is 2. So f of x approaches 2 from the left side. As x approaches 3 from the positive side, so that'd be the right, okay, so as you approach x3 from the right side, you fall in this open circle. What's the y value there? You approach 4. Okay, so it says determine the y values that each piece approaches from the left and the right of x is equal to 3. So we just showed that from both sides they approach different y values. Okay, this right here shows, wait a minute, that means they don't meet at that point. There's going to be a jump. So we're going to show it as x approaches 3 from the negative side, f of x will approach, this is an absolute value, right? So plug in 3 here, you'll get 3 plus 3 minus 4, which approaches 3 plus 3 is 6, absolute value of 6 is 6, so 6 minus 4, which then approaches 2, so we just showed it algebraically, okay? And as x approaches 3 from the positive side, f of x will approach from the positive side, that's this piece right here, so we plug into this guy right here, the bottom one, that'll be negative 1/3 times 3 plus 5, negative 1/3 plus 3, that's 3 times 1, which is 3, 3 over 3, 1, but it's negative, so it approaches negative 1 plus 5, which is 4. Okay, so we just showed that's what it approaches, a y value. So then you could say, since both pieces approach different y values, then f of x has a jump discontinuity at x is equal to 3. Okay? So we're going to do that for g of x, h of x, and p of x. So pause here, write this one in, and we will resume. Noticing it looks like I didn't even finish that there. Okay. So the type of discontinuity and x value where it occurs. So g of x, we're looking at the second graph here. Okay, so the x value we're talking about is negative 3, and it looks like it's a jump, right? At negative 3, we're going to say jump at x is equal to negative 3. Oops. Is g of x defined at this x value? If so, what is the y value? So let's check. Right, the first piece we had open circles and there was no it wasn't in the domain. Here now at negative 3 we have an open circle but also a closed circle here. That closed circle is being showed right here in the domain. X is less than or equal to negative 3. Right here x is only greater than negative 3, it's not equal to it. That's this open circle here. So it's in the domain of the first piece, so it is in the domain of g of x. Okay, so then we'll say we could find g of negative 3. We plug into the first piece. Okay, which is negative 3 plus 6 is 3. 3 squared is 9, but it's negative 9 plus 7, so you get negative 2. Okay, notice that's where this closed circle is at. Negative 3, comma, negative 2. Okay. Next one says the first piece stops at, right, first piece clearly stops at x negative 3. And the second piece begins at, starts here, right, same x value, negative 3. End behavior, as x approaches negative 3 from the negative side. So if you are on the left side of it, that's the negative side, you approach negative 3 here, that's this point, the y value is negative 2. But as you approach negative 3 from the positive side, that'd be this piece here. As you approach negative x negative 3 from the positive side, you end here. The y value there is negative 4. Okay, so says determine the y values that each piece approaches from the left and the right of x is equal to -3. So showing this, you're going to say as x approaches -3 from the negative side, g of x will approach negative, that's the top piece, that's the one on the left. Okay, so you plug in -3. We already showed this part for the most part in question 2, right? That'll be -9 plus 7, which then approaches -2. And as x approaches -3 from the positive side, g of x will approach, you plug in -3 now to the second piece here. That'll be the negative square root of -3 plus 3 minus 4. -3 plus 3 is 0. Square root of 0 is just 0. So then it's just 0 minus 4, which then approaches -4. Okay, so it matches there. The y values are different, so you could say since both pieces approach different y values, then g of x has a jump. Kind of lost my neatness there. Has a jump discontinuity at x is equal to -3. Okay, so we just showed they approach two different y values, so then there has to be a jump discontinuity. Okay, so then next one, we're going to do h of x. So we're going to answer the same questions here for h of x. So pause here so you can write this in, and we'll continue. So h of x is the third graph here. So this time they'll be meeting. They do meet, there's no jump, right? But they're meeting at an open circle. So we're going to show what does that analysis look like, how we did the first two. So first question is the type of discontinuity and x value where it occurs. That'll be a point at x is equal to -1. It's happening at -1. X -1. Here it is. So, is h of x defined at this x value? If so, what is the y value? So, is there a point on h of x where there's a closed circle? Graphically, there isn't, right? Looking at the domain here, there's no, in either piece is x less than or greater than and equal to it. It's not. So then, p of -3 is undefined or equal undefined. Oops, misspelled this. The first piece stops at, you can see here, right? It stops at x -1, and then the second piece also begins at x -1. So then -1 there. Fourth question, as x approaches -1 from the negative side, what's the y value? Okay, so if you approach -1 from the left side, you approach -1, x -1, you approach y1. Okay, that would be the point there. As you approach x -1 from the right side, you also approach the same open circle at y +1. Okay, so the end behaviors here, not the end behaviors, but the behaviors of the graph here, okay, approach the same y value of 1. So Determine the y values that each piece approaches from the left and the right of x negative 1. As x approaches negative 1 from the negative side, h of x approaches, right, plug into the top one here, negative 1, so then that'll be absolute value of negative 1 plus 4 minus 2, which approaches negative 1 plus 4 is 3, absolute value of 3 is just 3, 3 minus 2, that'll approach 1, right, should match this one there. And then as x approaches negative 1 from the positive side, h of x approaches, now you'll plug negative 1 in to the bottom piece here, so then h of x approaches, that'll be negative 1 minus 1 squared plus 5. Negative 1 minus 1 is negative 2. Negative 2 squared is 4, but it's negative, so then negative 4 plus 5, which also approaches 1. So you'll say, since both pieces approach the same y value of 1, but h of negative 1 is not equal to 1. It's not, because it's not, whoops, did I put p of negative 3? Sorry guys, this should be negative 1. H of negative 1, I put p again, sorry. That's the next one. H of negative 1 is undefined, right? There is no closed circle or point on the graph for negative 1. It's an open circle. So, but h of negative 1 is not 1, then h of x has a point discontinuity. At x is equal to negative 1. So we just showed they approach the same y value from the left and the right, but it's an open circle because it's undefined, and because it's undefined, then it's an open circle, so then it's point discontinuity. Last one here, p of x. So p of x is the fourth graph here in the bottom right, and it is 3 pieces. So here's the first piece, then here's the point, right? That'd be the second one, and then the third one is the absolute value you see here. So the type of discontinuity and x value where it occurs, that is happening here, here, that's at x negative 3. So notice too that they are two of the pieces are meeting at an open circle. The closed circle is somewhere off, so that's still a point discontinuity, and it's happening at x negative 1. So then, is p of x defined at this x value? If so, what is the y value? This time for x negative 1, negative, why am I reading this wrong? Sorry guys. It's at negative 3. Negative 3. This time, for p of x, negative 3, there's a closed circle, so then it is defined for p of negative 3. P of negative 3 is equal to, what's the y value at that closed circle? It is negative 2. So again, apologize for the mistakes here. They're meeting at an open circle at negative 3, but there is a closed circle on the graph. At x negative 3, the closed circle is at negative 2 for the y. Okay, so the first piece stops at x is equal to, so then this piece stops at -3, and then of course it begins again. There's a closed circle, but then it begins again, still at -3. So then those would be -3. As x approaches -3 from the negative side, so then you're traveling here along the negative side, you will end at the open circle because the road ends. There's like a big gap, right? That's at y2. And then from the right side, as you travel through here, you're going to end here again at the open circle at y2. So then that's what you would say there. Determine the y values that each piece approaches from the left and the right of x is equal to -3. So as x approaches -3 from the negative side, p of x approaches this piece here is this equation here, so plug -3 in there. That'll be 1/3 times -3 plus 3. So -3 times 1 is -3. -3 divided by 3 is -1 plus 3. -1 plus 3 is 2. And again, that's the y value where we're at. That's what we said here as well from the negative side. Then you'll say as x approaches -3 from the positive side, p of x approaches the positive side would be this piece of the graph here, which is represented by the bottom equation. So then that'll be the absolute value of -3 minus 1 minus 2, which approaches -3 minus 1 is -4. Absolute value of -4 is 4. So 4 minus 2, which approaches 2. So they approach the same y value from the left side and the right side. You'll say since both pieces approach the same y value of 2, but p of -3 is not equal to 2. P of -3 is -2. P of -3 is this closed circle at y -2. Okay. Then P of x has a point discontinuity at x is equal to -3. So, oops. Not only do they have to approach the same y value from the left and the right, but the function should also be equal to that y value when you evaluate for it. If it's not, if the y values are different, then you have a jump. If they're the same, you just need to make sure that at that x value, the y value is still a point on the graph. If it's not, then you have a point. Okay, so then moving on from the graphs, the next page of our notes is this one right here. This one right here. So pause it. We're going to generalize in this page what we just did. So general conclusions on continuity and discontinuity. If there's continuity at x is equal to a, then one thing for sure is both pieces approach the same y value call it b, right? And then 2, if there's continuity, if you evaluate for that xa, right, continuity at x is equal to a, then you'll get the same y value. So then that's a closed circle. The two pieces meet at a closed circle, so it's continuous. However, if you have a jump discontinuity, right, both pieces must approach different y values. You can also say, right, because if the y values are different, then obviously it's jump. But what about f of a? Well, f of a may or may not be defined. One of those end pieces, in other words, could be a closed circle, or they might both be open circles. It doesn't matter. If the y values are different, automatically you have a jump discontinuity. For a point discontinuity at x is equal to a, you could say both pieces must approach the same y value. I'll call it b. However, when you take whatever, right, at x is equal to a, if you take f of a, then it will not be equal to b. It will be equal to some different y value. So, like I said earlier, we can determine continuity or what type of discontinuity just given the function equation. So that's what we're going to be doing here to wrap up this lesson. For the following, determine the values at which the graph could be discontinuous, then determine if the function is continuous, and if it is, classify as jump or point discontinuity. So it's for the most part taking the bottom question of the 4 we answered for. So for this one, let's determine what y values they approach from the left and the right. As x approaches -1, pause also, sorry, so you can write this in. But anyway, as x approaches -1 from the negative side, x less than -1, so this is the negative side, g of x approaches, plug it in, so then -1 plus 4 is positive 3, 3 squared is 9, -9 plus 3, -6. So then let's check the right side. So as x approaches -1 from the positive side, g of x approaches, that's the second piece, that'll be absolute value of -1 plus 3 minus 10. -1 plus 3 is 2, absolute value of 2 is 2, 2 minus 10, hang on, this is incorrect, I put plus 3, sorry guys. -1 minus 3 is -4, absolute value of -4 is 4, 4 minus 10 is also -6. So we just showed then both pieces from the left and the right approach the same y value of -6. So that means graphically they're meeting at a point that has a y value -6. What we need to check now is, well, is that a closed circle or an open circle? So is it continuous, or do we have a point discontinuity? So you'll say, since both pieces approach the same y value of -6, right? But just by looking at the domain here, x is never equal to -1. So they meet at a point that has a y value -6, but just by looking at the domain, we know then it's going to be an open circle. So, but g of -1 is not equal to -6. Then g of x has a point discontinuity at x is equal to -1. Okay, so let's keep going. Number 2, here's this one. So let's determine, is there discontinuity at x -1? So again, first thing is check what y value we're approaching. So -1 from the left side, That's the first piece. This one, plug it in. That'll be -2, absolute value of -1 plus 3 plus 2. Okay, so then you'll have -2 times -1 plus 3 is 2, absolute value of 2 is 2, then the plus 2. -2 times 2 is -4 plus 2, so that approaches -2. And then as x approaches -1 from the positive side, that's the bottom piece here, absolute value of -1 plus 3 minus 4. -1 plus 3 is 2, absolute value of 2 is just 2, 2 minus 4. So it also approaches -2. So both pieces approach the same y value of -2. So then we'll say, since both pieces approach the same y value of -2. Okay. Also, the domain shows that for -1 there is a point on the graph, because right here x is greater than or equal to, okay, this part right here. So g of -1 equals -2. We don't need to show this, we already did right here for the bottom piece, right? It's equal to -2. Then g of x is continuous at x is equal to -1. That means both pieces of the graph then will meet at a closed circle. Alright, final page. Here, write this one in. Notice too that there's 3 pieces, so we're gonna have to take 2 sets of approaches here, one for x3 and one for x equals to 5. So maybe we could do one here, the bottom one here, and our conclusion here. So first one, as x approaches 3 from the negative side, that'll be the top piece. Okay, that means then that'll be 2 times 3 minus 3. 2 times 3 is, whoops, this will approach 6 minus 3, which then will approach 3. So then from the right side, that'll approach, the right side would be the middle piece. That'll be 3 squared minus 2 times 3, which will approach 9 minus 6, which approaches 3. So we just showed that they approach the same y value. Okay, since both pieces approach the same y value of 3, and h of 3 is defined right here for the middle piece. X is greater than or equal to 3, so it belongs to this one. There's a closed circle for x3, in other words, and f of 3 is equal to 3. Then h of x is continuous at x is equal to 3. Okay, so it exists. It's smooth there, in other words. Okay, now we got to do it for 5. For x is equal to 5. We'll say as x approaches 5 from the negative side, that'll be the middle piece. Plug it in. That'll be, whoops, not -5, +5. That'll be 5 squared minus 2 times 5. 5 squared is 25. Negative 2 times 5 is 10. So 25 minus 10 is 15. Okay, then let's check the right side. That'll be the bottom piece, the absolute value. As x approaches 5 from the positive side, that'll approach absolute value of 5 minus 3 plus 2. 5 minus 3 is 2. Absolute value of 2 is 2. So 2 plus 2, which approaches 4. Okay, they approach different y values. What did that mean again? That means they're not connected, so there's a jump discontinuity. So you'll say, since both, actually it fit, so you won't need to try to squeeze anything. Since both pieces approach different y values, then h of x has a jump discontinuity at x is equal to 5. Alright, last one. Sometimes you'll get problems like this where they're asking you for what values of a and b will the function below have point discontinuities, which I misspelled, discontinuities, at x is equal to negative 3 and x is equal to 2. So all you really have to do is just figure out what a and b have to be. A and B is found, in the middle equation here. So where will we make this have a point discontinuity? That means the y values have to be the same. They'll approach from the left side and the right side the same y value, but it's not defined, right? And it isn't. So what we could do first is try and solve for a and b. First thing is, from the left, if I plug in negative 3 there, right, that'll give me negative 6 plus 3. Oops, move this up, sorry. That'll give me negative 3. So from the left side, when x is negative 3, I get negative 3. For the middle piece, if I'm approaching it from the right side, then I'm plugging in for x, so then that'll be a times negative 3 plus 3b. That'll give me negative 3a plus 3b. Okay, so if we're gonna have a point discontinuity, then when I plugged in negative 3 here and negative 3 here for the first piece and the second piece, they have to approach the same y value. So I can set these equal to each other. Because I know they need to equal the same y value. Okay, so similarly, we're going to do the same case now for the other x value at x is equal to 2. So the middle piece for x2, that'll be a times 2 plus 3b, which will give me 2a plus 3b. And then for the last piece here from the right side, plug 2 in, that'll give me 1/2 times 2 squared times 3 times 2 minus 1. 2 squared is 4. 4 times 1 divided by 2 is 2 plus 6 minus 1. 2 plus 6 is 8 minus 1. That's 7. Just like here, the same idea. I know the two pieces need to equal the same y value. Here at x2, the two pieces from the left and the right side, if they're going to have a point discontinuity, then they have to equal the same y value. So then I know 2a plus 3b has to equal to 7. I have two equations that represent the same a and b. So I can set up a system of equations. I'm going to write this too, and I just changed the order here. Okay, and then I have the second equation I can set up this system here and then just solve and find a and b. I'm going to multiply, let's see, I don't know, I guess the first one. I'll multiply the first one here by -1. That'll give me positive 3a minus 3b is equal to positive 3. Right? If I add these two equations, that'll give me 5a. Those will cancel. Is equal to 10. And so a here, 5a is equal to 10, right? Divide by 5. A is 2. So I found a. And then, doesn't matter which equation you take, plug 2 into it. I'll pick the second one. So then that'll be 2 times 5 plus 3b is equal to 7. That'll give me 10 plus 3b is equal to 7. Subtract 10 from both sides. That'll give me -3. 3b is equal to -3. And then divide by 3. b is equal to -1. So that's how you would find these. If you plug a and b in, that's what would make this equation true for having a point discontinuity at x -3 and x2. Okay, so that wraps it up. That's concept 17, and it will be on your test, so study it. Small correction. So for this last one, right, I found a to be 2. And I plugged in 5 for some reason. Sorry, it should have been 2. That'll be 2 times 2, so not 10, but 4. Subtract 4 from both sides. That'll give me positive 3, and then 3 divide both sides by 3. That'll give me positive 1. Okay. Sorry, small correction there.